Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. And today we're looking at lesson 5.2. Again, we're looking at uniform circular motion in this lesson. And we're going to be looking at horizontal circles. What we'll do here is we'll go through a couple of problems, and then you'll see exactly step by step how you solve problems with these kinds of concepts of uniform circular motion. So we'll look at some of the equations that we use and problem solving techniques. So here's a typical simple sort of a problem, and it asks for find the tension needed for a 0.6 meter string to keep a 0.15 kilogram ball moving in a horizontal circle at 2.0 revolutions per second. Okay, so this is a typical kind of a problem. So we make our drawing here. It's fairly simple. There's not a whole lot that we need on here. We have our ball that's moving around in a circle like this. We have our force on there, and that'll be a tension force in the string, and it's toward the center of the circle of motion. We'll put some numbers on here. The mass of the ball is 0.15 kilograms. The radius of the circle that it's moving in is 0.6 meters. And they give you the frequency now, which is 2.0 revolutions per second. So what we probably want to do first, okay, because that's in frequency, we want to change that to period. And we use an uppercase T to represent period. Period means is how long does it take to make one complete revolution. That's period. Frequency is how many times does it go around per second or per minute, whichever the units you're using. And the tension, we don't want to confuse this with tension. This is period, which is the time that it takes to go around once. And so that's why we use force tension instead of an uppercase T to represent the force of tension in the string, so that we don't get them mixed up like I just did. So that's what we call the period, and the period is the inverse of the frequency. So it's 1/2, so 0.5 seconds. So it takes 0.5 seconds to go around once. So there's the info that we need, and guess what? We get back to F equals ma. So the force, the tension force that we need is mass times the acceleration, and in uniform circular motion, here is the acceleration of the object. It's the speed squared divided by the radius of the circle that it's moving in. So we can put that down. First of all, we don't have the speed yet, so we need to find that. And that's just simply distance over time, which is the distance to go around one circle divided by the period. So that's going to be 2 pi r. So that's the distance around once divided by the period. So I'll put the numbers in there now. And you can see the speed is 7.54 meters per second. So now we have speed. We can go back to this one now. And we can put the numbers into that equation, mv squared over r, which will give us the force needed. And that is, put the numbers in, the mass is 0.15 kilograms. The speed was 7.54, and that's squared, and divided by 0.6. So when you punch that in your calculator, you should get 14 newtons. So 14 newtons is the force, the tension force needed in order to keep that object moving around in a circle with those parameters there, the mass, the radius, etc. Right, so there's one simple kind of a problem with this concept here. And we'll go through one other one now. And so here's another one. So we have a car that's moving, and it's going in a circle, and we're given this information right here. So it's a 1,000 kilogram car. It rounds a curve on a flat road. The radius of the circle that it's making is 50 meters. Its speed is 50 kilometers per hour. And they want to know, will the car follow the curve, or will it skid off the road? Will its inertia keep it going in a straight line? So does it have enough friction force in order to keep it going in a circle or not? And they give us two different conditions. One is with dry pavement with a 0.60 coefficient of static friction. And the other scenario is with icy pavement where the static or the coefficient of static friction is 0.25. All right, so we'll go through this problem here now. So again, your diagram, and again, it's not too complicated. You have your your circle of motion there, you have your inward force, and in this case, the inward force toward the center of the circle is friction. So the friction of the tires on the road, and that's what keeps it moving in a circle. So the question is, do we have enough friction force in order to keep it moving around that circle with those parameters? So the information we have, it's a 1,000 kilogram car. Its radius of motion is 50 meters. It is moving at 50 kilometers per hour. And so right away, what we probably want to do before we do anything else is just change the units of speed to meters per second. So they give it to us in kilometers per hour, so we need to change that to meters per second. So to change kilometers to meters, we multiply by 1,000. To change hours to seconds, we divide by 3,600. And so our speed is 14 meters per second. So the vehicle is moving around that circle at 14 meters per second. And so that's the information there. And so now we'll go to F equals ma. And again, the force is mv squared over r. So what we'll do first is we'll calculate what force is required in order to keep it moving in that circle. And then we'll see if we have enough of a friction force in order to be able to do that. So the force that we need will be mv squared over r. So we can put those numbers in now. The mass of the vehicle is 1,000 kilograms. Its speed is 14 meters per second, and the radius of its motion is 50 meters. So that will give us a required force of 3,900. So if our friction force is more than 3,900, then we know that the car will not skid off the road. So that is, the 3,900 is the force needed to keep it moving in that circle. And now let's see if we have the friction force necessary in order to do that. So we know that the force of friction is mu Fn. So with dry pavement, we're given the coefficient of friction, and then we just multiply that by mg, and we'll see if we have enough of a force. So that's going to be m is 1,000 kilograms and g is 9.8. So on dry pavement, our coefficient of friction is 0.6. So our force of friction is 0.6 times 1,000 times 9.8, which gives us a friction force of 5,900. So the friction force of the vehicle, mu Fn, is equal to 5,900 newtons. So that's more than enough friction force in order to keep the car moving in a circle like so. So on dry pavement, we're good. So let's see if we're still good on icy pavement, where the coefficient of friction is less. So with icy pavement now, our coefficient of friction is 0.25. So we put that in there, we do our calculation, we get 2,500 newtons, which is not enough to keep it moving in a circle. So therefore, on icy pavement, with a coefficient of friction of 0.25, then the vehicle will skid off the road at a tangent to the circle. So therefore, your answer would be no. And as I was going through this, the circle I had here, it kind of seemed like there was a moon there. So anyway, there's a moon with somebody flying by.